Welcome to the AI Cafe today with our speaker, Mihai Gabriel Constantin. He's researcher at the AI Multimedia Lab University, Politehnica of Bucharest. Hello. Hello.
Hello. Hello.
Hello. Nice to see you and very happy that you're here. And his talk will be Deep Ensembles for the Prediction of Media Interestingness. I'm your moderator. My name is Carmen McWilliams. I'm from Grassroots Arts in Cologne, and this cafe is part of the European research project AI for Media. And we both, Mihai and me, are both partners in the AI for Media project. As always, please take notice that the session will be recorded. No confidential information shall be shared in this cafe session. In this cafe, the speakers express their personal view and opinions. This is not necessarily the official AI for Media project opinion. So great that also you come in. Welcome to all the participants in this cafe. It's always great that you take your time, come to us, listen to the speaker. And what is this cafe about? The Web Cafe offers a series of live webinars and sessions to give an insight into the European AI scene. Participants get the chance to share knowledge and experiences and meet stakeholders from various areas of AI research and application. So as it's interactive, I need your help out there. Please, let's find questions for the Q&A session. If you have questions to the presentation, please send it to us over the menu. And John asked already a question without even we have started. Will this be recorded? Yes, it will be recorded, this session. But as always, the speaker, in this case, Mihai Gabriel Constantin, has the right to decide if it will be online or not. So we can only really know in the next days. It will be always on the AI for Media archive. So now I introduce our speaker. Dr. Mihai Gabriel Constantin is a researcher at the AI Multimedia Lab University Politehnica of Bucharest, Romania, and got his PhD at the Faculty of Electronics, Telecommunications, and Information Technology at the same university. His PhD topic was automatic analysis of the visual impact of multimedia data. He has authored over 30 scientific papers in international conferences and high-impact journals with an emphasis on the prediction of the subjective impact of multimedia items on human viewers and deep ensembles, having a Google Scholar H index of 11. He participated as researcher in more than 10 European national or industry-based research projects, and he is a member of technical program committees and reviewer for several workshops, conferences, and journals, as well as organizer for several benchmarking competitions. So again, great you're here. Great. And thank you for being willing to be our speaker in the famous AI Cafe. So now I give you the floor. Enough of my talk. I will now switch the moderation to you. One moment, it always takes time. We have to give you the role. Yes, you should now have the capability of, yes, we already see it. Perfect.
Yes, okay. So, yeah, thank you for the introduction. And I want to thank everyone for being here and taking part and watching this presentation. I am Mihai Gabriel Constantin. I am a member and a researcher in the AI Multimedia Lab. What we do here is create a lot of models and methods for classifying and predicting concepts related to multimedia items, whether this means images, videos, audio, or textual information associated with them. Today I'm going to talk about deep ensembles for the prediction of media interestingness. Just a second. Okay, so we're going to start with some definitions regarding our domain. So what is interestingness? So far, a large number of traditional computer vision tasks address ground truth data that is objective, meaning the majority of annotators would agree with the ground truth. However, given the advent of social media that created huge collections of user-generated content, of user-generated media, this in turn created the need for new AI models that measure some different dimensions, that measure media's impact on the viewer. This again created the need for new tasks that address subjective measures of multimedia data. By subjective, we understand that some annotators may not agree with the ground truth data. There is generally a lower performance for methods that attempt to address such concepts. In particular because the ground truth is subjective and the subject is complex. There is also an inherent multimodality of this type of data, and sometimes there is a lack of clear features that define these concepts. Last but not least, these domains are generally more novel and are of, let's say, fewer papers address these subjects. So regarding visual interestingness, the definition that we will use for this presentation is related to how likely a media sample is to catch and maintain a viewer's attention. We must mention a difference here between social interestingness that is related to popularity and virality, and visual interestingness that is related to the visual qualities of a certain media item. There are a number of use cases for this concept, starting from curating large collections of media data and building better recommendation systems based on recommending items that are more interesting, but also creating better material for educational and training purposes, but also for promotional purposes. So moving on to the predicting media interestingness task. This was a task which was held at Medieval for 2 consecutive years. Medieval is a well-known benchmarking initiative that targets several tasks each year. It was developed in collaboration with Interdigital France. And during the benchmarking tasks, we had 33 submissions for interestingness prediction on images and 42 for video predictions. You can see here in the figure I'm showing you that the results for the systems, which are indicated by these bars here, are generally low. So we are talking about a mean average precision that is around 0.3 in the best cases. But it's also interesting to notice that human annotators, which are presented here in the red dots, also have do not have actually a near perfect prediction, with results going up to almost 0.7. So not even humans are able to predict this correctly 100%. What we saw during this was that late fusion systems generally have good performance, and this led us to develop some new ensemble systems. So ensemble learning or late fusion or decision level fusion, you will find it with one of these names in the literature, is an algorithm that starts with a set S of M media samples, which you can see here, and a set of N predictors, which you can see here. This creates a new matrix. So for each sample, there will be an individual prediction from each of the predictors. What ensemble systems do is to create a new function, f, that is able to output a new set of predictors, which we call O, that represent better approximations of the ground truth than all the individual inducers. The function f does this by combining the predictions of all the individual inducers in a certain way and creating a new output for that set. So, a few definitions. First of all, the set of predictors is also called inducers. The function that joins the results of inducers is called the ensemble engine. Now, inducers can be represented by any end-to-end approach, whether we are talking about a traditional approach based on, I don't know, SVMs, or we are talking about deep neural network approaches, or individual ensembles can even contain some smaller late fusion scheme. So far, ensemble engines usually are represented by traditional methods. So we can have statistical methods where, let's say, the weighted average of all the inducer predictions is used. We can have boosting methods such as adaptive boost or gradient boosting, or we can have bagging methods. So this means that so far there are, to the best of my knowledge, almost no approaches that use deep neural networks as the ensemble engine. So this is what we propose to do. So starting from a very large set of inducers, which are provided during the medieval competition, of course, with the help of the main organizers from Interdigital and with the help of the competitors that participated in the medieval challenge, we created a novel ensemble engine that is based on deep neural networks. We want to allow the deep neural network ensemble engine to learn the interactions between individual inducers and then encode the correlations between inducers, and again have the ensemble engine learn how these correlations work together. We call this network DeepFusion. So our DeepFusion network has 4 different approaches, and I'm going to start with the dense approach, which represents the basis for all the other approaches. Basically, here we want to use dense neural network layers in order to learn the way that inducers can interact. Of course, here we can look for an optimal configuration, and what we did in this case is have variations of the number of dense layers, variations of the number of neurons per layer, but also the presence or absence of batch normalization layer. This is just the way we decided to test these variations. Of course, other cases may imply other variations on this architecture. So the way that data goes through the network is shown in this figure. Starting on the left side from the input to the network, which for a media sample, let's say for an image, is represented by the predictions of all the individual inducers. This input is then passed through the network. Network which contains dense layers of variable size and of variable number, and batch normalization layers which can be turned on or off. After this data goes through the network, a final output will be created, which represents the ensemble's prediction for the given sample. Following this, we have an attention-based approach. This approach starts from the best performing dense architecture, which we basically got in the previous step, and attempts to augment it by using attention layers. We will use soft attention layers that would allow us to understand the importance of each individual inducers and, of course, turn them on or off, or practically give them a lesser weight in case their performance affects the overall performance negatively. Again, this figure shows how this architecture works. Starting from the same input as before, this is passed through the dense architecture and then moderated with the help of the attention layer. Again, the output of this entire network represents the final prediction that the ensemble created for this media sample. Next, we have the convolutional approach, which again starts from the best performing dense architecture and attempts to augment it by using convolutional layers. Traditionally, as you know, convolutional layers apply their filters over an image in order to obtain certain features. Certain features which are dependent on the spatial correlations between pixels in the input space. However, in our case, we will have to apply these filters in order to learn the way highly correlated inducers may interact. However, the problem here is that for any sample in our data set, there is no indication as to the correlation between the inducers in the input vector. What we must do in this case is compute the correlations on the entire training set and encode them in a new input, which we call a decorated input. So, starting from an input which contains all the predictions for the inducers, we basically decorate this input, each prediction in the input space, we decorate it with certain values. And these values are obtained as follows. We start from computing correlations between all the inducers for the entire training set, and for each inducer we decorate it with predictions from the most correlated inducers and with the correlation scores between the inducers. In this particular case, we do this for the 4 most correlated inducer pairs for each inducer in the input space. And thus we have pairs R1, C1, R2, C2, and so on until we have the 4 most correlated inducers. So this is how the input goes through the network. Again, it starts with the same input, which represents correlation, which represents predictions from our set of inducers, which we then decorate according to the algorithm I was talking about earlier. And then we pass through the convolutional filters. The result of convolutional filters is then passed through the dense architecture, and just as before, the output represents the prediction created by this ensemble approach. So a few things to notice here. For each sample, we start with an input space whose dimension is n, equals to the number of inducers. However, after decoration, we end up with a decorated space with a dimensionality of 3 times n and 3. After the convolution, we end up with the same dimensionality of n, meaning it is now ready to pass through a dense architecture, which we previously established to be the best performing dense architecture. Now, this will generate a number of additional parameters to learn. And in this case, we have 9 times the number of convolutional filters we will use, because of course it is possible to use more than one single convolutional filter in this case. Moving on, we have a new architecture which we called the cross-space fusion architecture. It again starts on the baseline created by the dense architecture. However, we identified several possible problems with the convolutional approach. First of all, when convolutional networks learn the way correlated spatial information is correlated, it uses the same filter over the entire image space. Moving on to how it will work on our particular example, when learning how correlated inducers interact, it uses the same filter over all the centroids, over all the inducers. And maybe there are some particularities between different centroids that convolutional approaches may not be able to understand. Also, it does not separate in a different space correlation scores from correlated output predictions, which may also represent a disadvantage. So what we decided to do is to create a new custom layer for this problem. This custom layer will be able to use different filters for each inducer centroid, and it will be able to go from a 3-dimensional space to a 2-dimensional, from a 2-dimensional space to a 3-dimensional space. We call this new layer the cross-space fusion layer. And first of all, let's start with the way we build this type of layer. So starting from the same input as before, we again expand this input in order to create space for the outputs of correlated inducers and for correlation scores. But this time we go to a 3-dimensional space instead of a 2-dimensional space. So regarding what happens at the first index in the 3rd dimension, we start by creating centroids, which again represents our initial input space. And we decorate these centroids with outputs from the 8 most correlated inducers with each particular centroid. Next, in the 2nd index related to the 3rd dimension, We start with a central value of 1 because an inducer is always 100% correlated with itself. And we decorate this with the correlation scores of the corresponding correlated inducers. We do this for all the items in the input space. And next we create the cross-space fusion filter. So started from the newly created decorated input, we pass this through the CSF filter, which will output for each centroid, so for each inducer in the initial input space, a two-dimensional matrix, which will contain the initial value in its center and several transformed values around it. In order to get these values, we will use the initial inducer value, the initial prediction, and a product between the correlated inducer predictions and the correlated score. Next, we define a set of parameters which we call alpha and beta. And we use alpha parameter in order to moderate how the initial inducer values affects the result, and the beta parameter in order to moderate the product. Of course, in this case, we will have 8 alpha parameters for each inducer in the initial input space and 8 beta parameters. So let's take a look at how this architecture works. Again, we have the initial input space, which is just as before. It's represented by the predictions created by the inducers, which we then decorate and create the three-dimensional decorated input and pass through the CSF layer. In order to obtain an input to the dense architecture that looks similar to the way the dense architecture was trained, we then employ an average pooling layer and send these results through the dense architecture. The output here again represents the prediction of this ensemble architecture. And again, some things to notice here. So for each sample, we will have an input space dimensionality of n, which after the decoration will be transformed to a three-dimensional input space of size 3 times n, 3, and 2, which after is passed through the CSF layers, through the CSF filters, will have a dimensionality of 3 times n and 3. As I mentioned, the role of the pooling layers is to reduce everything down to the initial dimension of n. So now this will create a number of additional parameters for the network to learn. This is 16 times n in total, meaning 8 times n alpha and 8 times n beta parameters. This isn't such a large number, and just as it was the case for the convolutional approach, this doesn't represent much of an overhead when training a network if we compare it with the initial training time of the dense architectures. Now, regarding our experimental setup, as I previously mentioned, we used the inducers that were published during the medieval predicting media interestingness task from 2017. Here we had 33 inducers for the image prediction subtask and 42 for the video prediction subtask. We thus created two splits based on a random stratified k-fold approach. The first one splits 75% of the data for training and 25% for testing, while the other one represents an equal 50-50 split. We repeated these splits in order to create 100 partitions, and this way make sure we don't fall in a partition that is basically just lucky for our type of approach, that favors our type of approach. So the values we will present actually represent an average over these 100 partitions. We also used some baselines here in order to test the DeepFusion approach with other traditional ensembling methods, and these are the results. So in this table, you can see the results for both image prediction and video prediction. The baselines are represented here in a lighter shade of blue, while the results of the DeepFusion systems are represented with a darker shade of blue. Regarding the baselines, we have here the best result from medieval, the best result from on the data set published outside of medieval, and a baseline which is based on traditional ensemble approaches. The best performing baseline of this type was adaptive boosting for both cases. As you can see, the results are very, very good. Even starting from the, let's say, from the dense approach, the results clearly surpass both the best performing results from the literature and the best performing results from for traditional ensembling methods. The rest of the approaches continue to upgrade the results. And for image prediction, we have a best performing results, a result of 0.34 for the 75% split and 0.24 for the 50% split. While for video prediction, we have mean average precision at 10 result of 0.28 for the 75% split and 0.16 for the 50% split. So as you can see from these two tables, the best performing variation of our network tends to jump around between the convolutional approach and cross-space fusion approach. So let's look into some observations regarding these systems. So regarding their significance, we have a 148% increase over the current state of the art on images and a 73% increase on videos. Furthermore, we have a 105% increase on images over traditional ensembling methods and 150% for videos. This is, of course, a very, very significant result. Next, can we apply this method to other concepts or to other domains? And in fact, we did that. And at the end, I'm going to present some some of our published papers with regards to this. So here we have for emotional content classification based on both the arousal valence space and with regards to fear detection, and violent scene detection, and finally medical captioning of CT medical images. Again, for these particular examples, again, our approach proved to be useful and to improve the overall results by significant margins. Next, regarding how we set up our method. Thus far, the parameters we chose to vary, like the number of layers, the number of neurons per layer, the number of convolutional filters, or how many correlated inducers are actually populated in the decorated input, show to be to vary from domain to domain, from concept to concept. So we cannot actually give a suggestion with regards to how to start training, except the fact that each of these variations have to be learned for each new data set or each new concept that you wish to study. So looking into how the inducers affect the performance of the DeepFusion approach, we find that it is most important to have a high number of diverse, or let's say uncorrelated, groups that contain in their turn correlated inducers. Another important thing to note here is that this approach brings meaningful improvements or meaningful results only if the results of the inducers are not already very high or near perfect, because applying such a procedure on inducers that are already near perfect or already have very high results may prove to have insignificant improvements or need too much computational power for how significant the results are. A few open questions regarding this approach. First of all, we would like to continue to look for the optimal CSF-like layer, let's say cross-space fusion version 2 or 3. We think there may be more optimal setups that we still haven't explored, and we would like to get into that. Next, given the high computational demand created by such approach, and this computational demand is derived from the fact that you would have to train and to infer using a high number of inducers. How can we filter out inducers and reduce their number as much as possible? So this is basically a two-part problem. First of all, can we perhaps reduce the number even before we start the learning procedure? And secondly, can we reduce their number after the learning is done and draw some conclusions based on the results of the learning process? And finally, let's say another step ahead in this direction would be to reduce the number of inducers at runtime. Basically, develop or have a sort of early exit architecture, let's say. But in this case, the early exit would just ignore inducers, not make them infer or process the input image. So as I mentioned, these are a couple of published works from me and from people from the AI Multimedia Lab. This is a nice place to start in studying either interestingness or our DeepFusion approach.
Yes, thank you. Thank you.
Thank you very much for your attention.
Thank you. Yes, thank you for a very interesting presentation and great. Now we got a deep dive
Sure.
into deep ensembles for the prediction of media interestingness. Can you summarize for a person like me or for some of the audience why it's such a difference between when you look at this huge difference in image prediction between DeepFusion and best medieval? I mean, to understand that somehow.
Okay. If I can just turn back to the tables.
Yes. Yes.
Yeah,
just
okay.
just try to tell even people who are not perfect engineers.
Okay, so basically the best result for medieval, this basically represents, in fact, all the results from medieval actually represent our inducers. So our system final performance is based on gathering all these inducers that were let's say submitted by participants to the benchmarking task and using all their power combined, and it creates such a significant difference because each of the individual systems, or let's say most of them, analyzed different aspects of the data. So some of them, let's say, analyzed the beauty of an image. Others analyzed audio components from a video sample, and so on. So yeah, basically this is what creates this big difference. The fact that it can exploit each system's, each inducer's individual advantages.
Okay. Thank you. So again, please, every participant out there, if you have a question, please send it to us and don't be shy. Everything is fine. You saw I can also ask simple questions or difficult questions. It's all fun. So now next question for me. What could be, in your eyes, the most exciting application service based on your ensembling-based architecture?
Okay, so going away a little bit from, let's say, the interestingness side or the prediction of subjective concepts, I think that the best, let's say, domains to apply such an algorithm is either domains where the results of individual systems are not yet good enough, are not yet, let's say, market ready, and by using such a method we would allow them to be market ready, or systems where it's very important to have an accurate prediction. Here I'm thinking of I don't know, maybe critical infrastructure systems or let's say applications like that.
Yeah. And this would be, just give an example for this not good enough for market ready. Who would be these people? I mean, we just have to understand it. It's communication. Who would be this? Who would use that? I mean, which company or?
Okay. Yeah. So as I mentioned, the initial benchmarking task was actually done with Interdigital France.
Yes,
which it's they are also in the AI4Media project with us, and their use case was very interesting. So they wanted to know which images or which video fragments from a large collection of images would be most interesting to use in order to promote a Hollywood-like movie. So basically what they wanted to have at the end the benchmarking task was a system that would allow them to create better, let's say, promotional material for a Hollywood movie. But of course, this can be extended to news items, to educational material, and so on.
Yeah, but now I completely understand. I think you made the circle of understanding. Because we know also interdigital, there's many people who have been working for Technicolor before, and it was about interactive TV, and they're very much in Hollywood productions and trying to predict what the consumers at the end like to watch, no? And what would attract most people. And so it's very nice to predict this somehow and find ways with artificial intelligence to basically,
Yes, actually, our collaboration with them started when they were still Technicolor, so before the merger took place.
No, but I just put it in a picture, no? To understand. And that means like we are all AI for Media partners, but we are long-term partners in many research projects. So I think the community out there who's listening today understands. And I have another question. So, of course, this is now going in the area which is very fashionable in the moment, is trustworthy AI. What could be trustworthy and so on. So you have an example of trustworthy media recommendation prediction today. Is there something out there which we can trust?
Right. So basically, this is what we are working on at this moment. We are trying to create trustworthy systems that are based on this type of approach, let's say. One of the planned collaboration is actually in the recommender systems domain. So so the way we're trying to handle, let's say, trustworthy AI is, well, first of all, of course, by increasing how robust systems are. So having better results generate better results that are closer to the ground truth. But also we consider this to be an interesting approach, again, for future developments into the explainability part of trustworthiness. And what we are thinking of in this case is having a final neural network layer, let's say, that will present a correct explanation with regards to which of the inducer systems have contributed more to the final result. In this way, we can perhaps say regarding an image that, for example, in order that image was considered interesting because it had the right colors, the right combination of hues, and you know, all these kinds of combinations.
Yes, I mean, it's a hot topic, no? As too many people fake things. I mean, we know politically there's horrible things going on, so so it is always the same thing. It can we trust these images? Can we not trust them? Is there any way for users, for companies, for anybody to figure out, organizations, no? What is trustworthy, what's not? So there's a huge application area, no? I mean, huge area of finding out is.
Yes, it's a huge area, and it basically represents one of the directions we are heading into now with the, let's say, next version of DeepFusion.
Yes, and also I make a little bit advertisement for AI for Media. I mean, that's the key of the whole thing, is to make media itself more trustworthy and fight fake news and so on. Yeah, here comes the question from an audience member, which is great. Thanks out there, Alison. You mentioned at the beginning that ensembles are typically created using traditional models, SVM, regression, etc., instead of deep learning models. Do you know why this is?
Yeah, okay. Yeah, as I mentioned, in that case, I was talking about the ensemble engine. So about the engine that takes all the output from the inducers and gathers them and creates the final result. So I think one of the most important aspects here was that there is a lack of data in this direction. So actually not necessarily a lack of data, but a lack of inducers. In order to do something like this with a large number of inducers, one would need to design and develop them individually. However, once we organized the benchmarking task, this allowed us to use the community to basically take the inducers the community has created and using them in this type of approach. One more thing here is that if we if someone would develop deep ensemble like approach with a very low number of inducers, that would probably not work best under a deep setting, and a simple statistical ensemble would probably work without having too significant improvements. So the improvements would most likely be small.
Okay. So I will close now the question answer session. If not, somebody screams in the chat or in the questions, I need more answers. No, but you can still say something else. As you know, there is a recording going on. I said already in the beginning, this evening, I will send it to you. Gabi, I am allowed to tell, not me, Gabriel. I send it to you, and then you decide if you want to publish it.
Sure.
As I mean, I publish it, but you just give me green light, so we are totally secure. And recording, if you out there, members, participants in this cafe, if you want, please contact Mihai or contact me. I will forward it to Mihai, to Gabi. Mihai, Gabi, it's difficult. For me, I always take the first name, but it's actually Gabi. So yeah. So okay, this was a great presentation. I thank you very much, and I wish you a nice afternoon to you all, to you, and
thank you, and thank everyone for being here and listening to my presentation.
Yes. So bye, and maybe see you in person. There is a chance again in life.
Hopefully, yeah.
Okay, bye.
Okay, bye.